Alright, hello and welcome to another video by me. Yeah, alright. I think it's about time that I use the video to talk about some of the things that I really haven't spent that much time on, but probably is quite crucial for the discussions we're doing. That is the questions about what is science anyway, right? I claim that we should be doing scientific discussions, but I haven't really spent that much time on really sort of trying to nail what science is. Now, this is my view on it. This is not straight fact. It is not something that you can hammer on your wall and say that's how it is. This is my personal view. You might have people that would tell you otherwise. I might be wrong. Hell, if I'm wrong, I hope someone would write it on my channel and say it. Of course, argue well for the case, but anyway. Alright, so the first thing I would like to say, and that is when we discuss the notion whether science is a constrained world where there aren't really place to think out of the box. Right, I think I've got that notion from some of you on my channel. Yeah, that's not true. But in order to address this question or this claim, you have to realize what science is and how science works. All right. So the first thing is that science is a collaborative engagement. It's a collaboration between all the scientists in the world, and possibly some of them who aren't scientists in a strict sense. That's the first thing. And the other thing is that science is an evolving arrangement. Scientific ideas, scientific knowledge evolves, and that is why we don't sort of always go back to, like someone claimed, we should go back to the beginning. We should erase the board and we should go all the way back to the beginning and start over again. And that is not a good way to get good knowledge, right? Because every time anyone claimed that we should do that, then we will start right over. So that is why in science we build on what is already accepted. And that is also why you can't really make that wild claims, because your claims or your hypothesis or your ideas have in some way have to be in agreement with the current knowledge that we have, at least the one that is accepted. All right. So that's one thing I would like to state right away. I think I sort of have said it sometimes in some videos, but not like this, not in a strict sense. All right. The next thing is, and that's something I have written here. It's about my interpretation or my idea on what I would say how science really works. All right. So the first thing is that you get an idea. Now this can be anything. Really, I mean it. Anything, even a flat Earth. All right. An observation, crazy thought. If theoretical physicists didn't have crazy ideas, right? Like string theory, M theory, it's the same. Multiverses, the idea of using, what do you call it? The idea of using a warp drive from Star Trek, actually trying to design a warp drive in reality. Now, whether or not this is possible to construct at the moment, that's quite irrelevant, because what those people, in particular, I think it's a guy called Miguel Alcubierre, have shown is that it is physically and mathematically a sound idea. All right. So no. You can really think way out of the box in science. But the thing is, and that's what we come to now, is that when you have this idea, you have to sort of formulate this as a hypothesis. And that is where you put it into a mathematical and physical framework. again, this is where you really try to see if your idea is invariant or consistent with the current knowledge, and then you try to see, well, can I design a mathematical representation of my idea that can be proved, right? That the math had to be proven on, at least have to work out. All right. And then comes the crucial part. Now some theories get to this point. This is not entirely true, because in theoretical physics you would sort of say that if you have an idea and you can put it into a mathematical and physical framework, and this really pans out, this calculation you have done, then you would call this theory. But in order to make a broader statement on how science works, I would put it like this. Alright? So when you have this hypothesis, it might stand here for many years, because your hypothesis might not be testable with the current hardware, the current machinery that we can use. But in any case, then you come to the part where you do experiments. Lots and lots of experiments. Try to test your hypothesis from different angles to see if it really pans out, if it's a good hypothesis. Alright? Then you publish your result, and then comes the peer review. That is where other scientists can take your article, right? Read it and say, oh, that's how he did it. Let's go down and test it in the laboratory, or let's recalculate this, let's look the numbers through, sort of, so on, right? Then they can say, well, it's okay. And then your article will be published in a scientific journal, and then comes probably more experiments. You again have to test this idea from different angles. You have to challenge the idea. That is what science do. That is really, especially what physics do, and science in general. We take these ideas, these hypotheses, and also theories, and then we test them and test them again from all sorts of angles in order to make entirely sure that this is really a theory or an idea that has been thoroughly tested. Right? And when all of these things have been successfully done, gone through, then you can say, well, we might actually have a working theory here. We might actually have a theory that in a scientific sense makes sense. It's a good theory. But you have to do this, right? And in essence, even when you have theoretical physics, the number one way to test if a theoretical physicist theory is consistent, or not true, but is a good theory, is to see if you can design an experiment to check it. And from what I know is that in CERN, you can watch the a video from CERN. I'm not sure, I can't remember what it's called. It's on Netflix also. I think it's called Particle Fever, actually. But in sort of summing it up, you have two competing theories. You have multiverse, and you have I think it's string theory. No, I think it's actually it's supersymmetry. Sushi. Sorry. Alright, and from what I remember in my head of seeing it, is that for the multiverse you would have a Higgs, a mass of the Higgs of about 150 MeV, and for the Sushi you would have a mass of the Higgs of about 115, I think it was. And so these are two competing theories. It's theoretical physics, right? It's basically math and good ideas, really good ideas, but it's good ideas, right? And of course it has been tested in peer review, and from that gained the prestige of being a theory. But in any case, so what did they do? Well, they tried to find the Higgs particle in CERN. Now that's a way to test these two theories, right? And what's really interesting here, and that's what I find really, I find it really interesting, is that as far as I remember, the mass of the Higgs was actually found to be somewhere around, I think it was 125 MeV. So it's sort of between those two theories, maybe a bit closer to supersymmetry. But in any case, that's an idea how you would test this kind of theoretical physics theories. All right. Yeah. The other notion, I think I've gone a little into it, is that scientists do really think out of the box. I think I've shown that now, or just at least argumented for it. But those scientists that think out of the box are also often refuted. Their ideas are refuted because either they are not, the math really doesn't fan out, or they simply are not consistent with what other scientists have experimented with and found other results, or results that simply was consistent with what was claimed. And then another notion I've found, on, I think I've got the impression on my channel, is that some of you somehow think that scientific theories aren't challenged, right? That our current knowledge aren't challenged. And that's basically, I think it's because you want to claim that the Earth is flat, right? But that's not a true claim. I remember, now we're talking about CERN again, is that a team at CERN found superluminous neutrinos, or that's at least what they thought they had found, right? What would superluminous theories mean? Well, I can recall a certain person called Einstein that said that the maximum velocity in the whole universe, in any case, for a particle with mass, a particle in any case, is the speed of light, right? So a superluminous, that means a particle faster than light, neutrino, that would sort of violate Einstein's special relativity. So no, scientific theories, even the ones we claim that not true, but certainly has been accepted as our current accepted knowledge, are certainly challenged. Alright, then the final two things I would like to talk a little bit about is that, and this might come to a surprise for some people and may also be, well, a bit controversial, but I think that a flat Earth really makes common sense. Why wouldn't it, right? When I go out of my door every day, when I go to the university, I see that what I walk on is pretty flat. Now there may be small bumps and hills, and so it maybe go up and down, but in general, it's flat, right? It's just flat. So the notion, the perception of the Earth being flat is not stupid. It's really not stupid. What I do believe is stupid is the flat earthers that think that in order to make their ideas, or the idea of the flat Earth, in order to make the money fit, in order to make it fan out, they sort of say, well, we have these observations here, that's on Earth, small observations, what I can do with my own eyes, or whatever they might throw at you and say, see, this proves, or at least, yeah, this suggests that the Earth is flat. But those data we have here, some of them is from NASA, but also other places, they are either constructed or faked or something like that. It's CGI. It's anything. They sort of have to build this enormous conspiracy up in order to make the Earth flat, and I find that really silly. But the main idea that the Earth is flat, I think that's reasonable to a certain degree. Now, one particular person on my channel said that we have somehow been taught that we should not trust our senses, right? So it's sort of, I've sort of written the other claim on my paper, we should trust our senses. And I would say, yes, you certainly shall trust your senses. Of course, why shouldn't you? But you shall also apply them correctly. That's the key, right? So when I go out and look around, and I see that everything around me is just flat, that's where I'm wrong if I just infer from that notion or that observation that then the Earth must be flat all the way around. And let me try just here the last part of this video, or the second part of this video, depending on where I cut it, to sort of give an idea of why that might be. Now, this idea really comes from sort of a way in high school math to describe, for example, derivatives. All right. So you take, you know, I assume that many of you have seen this here, where you put up a curve, right? Then you want to know how much does this, what's the deflection, or what's the angle here, right? Yeah. So how do we find that? How do we find the angle on a line at what point? At one point. That's tough, right? So the main idea is what if we put a point here? Then we can make a straight line. But that's not really the angle here, right? All right. Let's put the point here instead. And it's closer. What if we put the point here? Then it's even closer. And here it's even closer and closer and closer. And this is what we call sort of an infinitesimal approach, right? We get closer and closer and closer and closer until the distance between those 2 points are infinitesimal. And then we can do a derivative. The idea of seeing why the Earth might be perceived as flat, it's sort of the same basic idea. So let's say I draw up a circle here. It might not be perfect, but I hope we can all agree that this is a circle, right? This is a circle. Alright? Let's zoom in on that circle. So let's take a small portion up here and blow it up. Not like a bomb, right? Make it bigger. Then we might see something like that, probably, right? A little arc, all right? So let's expand that. Then we might see something like this. It still arcs, but it's been flattened out a bit, and that would be reasonable when you zoom in on a circle. Then we take a bit here. Just make a line down here. Then we get something that is even flatter. Then we zoom in again on this little box here, right? We get something even flatter. And then if we zoom in at this point here, we would probably see, if that was Earth, probably see something like this, depending on the zoom level, of course, but come on, work with me here. So even though this is a circle, the closer you get, the more it will be perceived as a flat line, as a plane, right? Another idea. Let's just do a quick calculation. So what do we know? Well, let's say we want some sort of relation between an average person. Let's take a person like me. I'm just about 2 meters high. I'm 187, but let's give it sake. It's easier to just say 2 meters. And then compare that to the radius of the Earth. Okay? So we say, well, we have me, I'm 2 meters high. Then we have Earth, I think it's 6,371 kilometers, so that is 6,371,000 meters. Let's calculate that to get a relation. Let's first of all just agree that this will be a number without any units. Alright? Unitless. Because meter divided by meter, that's nothing. Right, 1. Let's see. 2 meters divided by 6,371,000. That is rounded 3 times 10 to the minus 7. 3 to the 10 to the minus 7. Alright. Now, you probably all, some of you, hopefully all of you, have seen what those big gym balls, right? Not gimbals, but gym balls. The one you can use in the gym to do all kinds of exercise, and you can lie on them on the back and on the side, whatever you want to do. Now, I've seen such a ball. It's just about, I think it's about 50 centimeters in radius. I think that's reasonable. So this size, right? So 50, yeah, I think that's reasonable. So how big would I have to do? Sorry, how big would I have to be if I were to be standing on that ball, but in the same size relation as me standing on the Earth? Let's calculate that. Now, first of all, since this is unitless, I don't have to convert anything. So I can just say that, well, I have these 50 centimeters in radius. I multiply that by this number, 3 times 10 to the minus 7. And that gives me 2 times 10 to the minus 5th centimeter. 2 to the minus 5th centimeter. I think that is 0.5 centimeter. Something like that. I'm not even sure what that is. It's really small. I don't think I would be able to produce anything that I could show you. I don't think I would be able to produce anything of that size in any way. But I certainly won't be able to produce something like this that I could show you standing on top of that ball, to show you on a video. So that's just to put into sort of perspective what kind of enormous sizes we're talking about here, right? So for that person, for a person that is 2 to the minus 5th centimeters high, standing on a ball with a radius of 50 centimeters, I think he would perceive his surroundings as pretty flat. Yeah. Then there's the notion of the curvature of Earth, the 8 inches per mile squared, or whatever you call it, and sort of, I will address that in a later video. But for now, let's just stick with this and agree on that when we discuss in the future, we have a basis for what we are discussing and how we are discussing it. Thank you for watching.